Lecture 7.5, Day 2, Fluid Pressure and Forces. This is one of the smaller fish tanks at the Georgia Aquarium in Atlanta, Georgia. The Georgia Aquarium is definitely worth a visit if you are in the area. What is the force on the bottom of the aquarium? Force would be equal to the weight of the water, which would be density times volume. In this case, we have 62.5 pounds per cubic foot times 2 feet times 3 feet times 1 foot, or 375 pounds. This would be an example of why you usually empty a tank before you try to move it. If we had a 1 foot by 3 foot plate on the bottom of a 2 foot deep wading pool, the force on the plate is equal to the weight of the water above the plate. We have density, which is 62.5 pounds per cubic foot, times depth, which is 2 feet. Density times depth makes pressure, times the area, which is 3 feet times 1 foot, or 375 pounds. All the other water in the pool doesn't affect the answer. If it did, then your toe would immediately be crushed when you dipped it in the Pacific Ocean. What is the force on one end of the aquarium? Depth and pressure are not constant. If we consider a very thin horizontal strip, the depth doesn't change much, and neither does the pressure. The force at y is 62.5 times y times 1 dy, where 62.5 is the density, y is the depth, and 1 times dy is the area of the thin rectangle, which we're using as a strip. The total force then, added from 0 to 2, is the integral from 0 to 2 of 62.5 times y times 1 dy, which comes to 62.5 over 2 y squared, evaluated from 0 to 2, or 125 pounds. Here's another example. A flat plate is submerged vertically as shown. It is a window in the shark pool at the city aquarium. There's our shark. Find the force on one side of the plate. So what we want to do is draw a horizontal strip of constant depth. The depth of the strip can be determined if we use this axis. The distance from the top of the water to the x-axis is 5 feet, and from that 5 feet we need to subtract the distance from the x-axis to our strip, which is y. So the depth becomes 5 minus y. The length of the strip can be determined using the equation of the line that represents the side of the glass plate, y equals x, so x equals y, and the length then is 2x or 2y. The area of the strip then is length times width, or 2y dy. The force at y then is density times depth times area, or 62.5 times 5 minus y times 2y dy. Adding up all the strips, we get the integral from 0 to 3 of 62.5 times 5 minus y times 2y dy. We factor out the constants and clear the parentheses. Then find the antiderivative and plug in the limits of integration to get the total force on the plate, which is 1,687.5 pounds. This example explains why the glass on a commercial aquarium is so thick. In this problem, we could have put the origin at the surface, but the math was easier this way. Normal distribution. For many real-life events, a frequency distribution plot appears in the shape of a normal curve. This is also sometimes referred to as a bell curve. Examples are heights of 18-year-old men, standardized test scores, lengths of pregnancies, time for corn to pop. In fact, there are an infinite number of examples of real-life situations that can be modeled by a normal curve. The mean, mu, or x-bar, is in the middle of the curve. The shape of the curve is determined by the standard deviation, sigma. So there we have mu, x-bar, and sigma as terms to know. A normal distribution follows the 68, 95, 99.7 rule. That is, 68% of the data falls within one standard deviation of the mean. 95% of the data falls within two standard deviations of the mean. And 99.7% of the data falls within 3 standard deviations of the mean. The area under the curve from A to B represents the probability of an event occurring within that range. In Algebra 2, we used z-scores and a table of values to determine probabilities. If we know the equation of the curve, we can use calculus and our calculator to determine probabilities. The normal probability density function, or Gaussian curve, is f of x equals 1 over sigma radical 2 pi times e to the quantity negative x minus mu squared divided by 2 sigma squared. The good news is that you do not have to memorize this equation. You could predict probabilities by integrating this function to find the area under the curve. In real life, statisticians rarely see this function. They use computer programs or graphing calculators with statistics software to draw the curve or predict the probabilities.